Okay guys, today we're going to talk about the memory hierarchy, and this is really important guys for the programming part. If we need to go to the programming part, you need to know those different types of memory. The memory hierarchy, you can draw it this way, and this is the easiest way. Here I'll have what? R sitting on top, meaning registers. Here we can say cache L1, cache L2. We can have also cache L3. Then we have RAM, and then hard drive. Registers. This is registers sitting on top, and cache. And what do we have? Cache L1, cache L2, RAM, and hard drive. We can have also cache L3 or cache L1 by itself. This is cache what speeds up, one way to speed up the computer. What are the registers? Registers is the type of memory. It's the smallest in size and the most expensive. In assembly, in our architecture, we're programming using MASM, the AI32. We're gonna have 32-bit, 8 32-bit general purpose registers. And please guys, you need to know them. We have EAX, EBX, ECX, EDX, and ESI, extended source index, extended destination index, and I think stack, and what was the last one? I forgot. But those 8 32-bit registers, and I have 6 16-bit registers, and most important for us is the code segment register, a 16-bit register, and the data segment. And I have the stack segment register. All of those are 16-bit. I have 16-bit and 8 32-bit registers, and I have the GS and another 2 that are not important. I only need you to know those 2, but no in general. And I have 2 more registers, 2 more 32 registers. One of them is the E flag. E stands for extended. That's why it's 32-bit. At the beginning we had AX, which is a 16-bit. So that's why the E, we have E flag register. It's a 32-bit register that holds the flags. This register, the CPU looks at it every clock cycle. It looks to see if any of the flags was changed. Some of the flags we have is the parity flag. We have a 32-bit 32 flags, let's say 32-bit 32 flags. Each time the CPU look, we have the carry flag, overflow flag, sign flag, parity flag, zero flag. For example, when the destination is 0, sign flag will be set to 1. Remember we said when we were adding binary and we had 8-bit added to 8-bit, and we had on the 9th bit an extra overflow or carry. This is where it goes to the flag register, and the CPU looks at this every clock cycle, so it will know that a carry or overflow happened or occurred here. If the destination is let's say negative, the sign flag will be set. Parity flag, sign flag. What other flags do we have? Those. If we have, sometimes when you have in calculations, if you have a number or number over 0. What does this equal? Do we have a value for it? A flag will be set here. E flag register, and I have another register, sometimes called as PC program counter or instruction EIP, extended instruction pointer, a 32-bit register which holds the address instruction pointer of the next instruction to be executed. The next instruction to be executed. Sometimes in other books you might see it. It's called PC, program counter. Holds the address of the next instruction to be executed. So I have 8 32-bit registers, EAX, EBX. You have to know this for the programming part. Then I have 6 16-bit registers, CS, DS, and I have 2 registers, EIP, extended instruction pointer, which hold the address of the next instruction, and the E flag, and both of them are 32. So total of 10 32-bit registers and 6 16-bit registers. Total of 16 registers. Why don't we have more than 16 registers? Why don't I have 100 registers? If they're the fastest memory, why don't I have 100 registers? Remember, registers are expensive, and here's how price goes. Price goes this way. This is price. Registers are so expensive. Then cache, then RAM. Price, size goes this way. Registers are small, cache is small, size grows that way, and this is speed. I don't know, can you see the 1 minute, let's go. So price, size grows this way, and price grows price, size, and speed. This is hard drive is slowest RAM, then, and remember, everything that runs on the computer has to run on the RAM, has to go through the RAM. Anything has to run through RAM. Can you run it from hard drive? No, you can, but there's a new technology. So another difference is, why do we have hard drive? Why do we have RAM? Why does everything has to run on RAM? Hard drive is, now where's your operating system residing? It's on your hard drive. But when you do boot, when it boots, where does it boot it? Boot from the boot sector, which is here, to RAM. Loads it to the RAM to run it. Everything has to pass through RAM to run it. This is what's called volatile or non-volatile memory. Meaning what? A volatile memory is in a computer is a storage that only maintains its data while the device is powered. If I have power, I'll maintain my data. This memory will maintain its data. When you turn the power off, when you take the plug off of a computer, all this will be gone. Any data on this memory will be gone. Those 4 registers, cache, and RAM. This is the type of memory. On hard drive, it's different. It's non-volatile. If you take the power off, the data is still there. Next time you power up, it's working and it's there. Think of if hard drive was volatile. What do you need to do each time? Each time you're going to need to load your operating system to hard drive. You need something to bring your operating system, either CD, an external hard drive, or you need something to load your everything will be wiped, nothing will be saved. And please guys, you need this. This is chapter 2, slide 16. Remember, registers and memory hierarchy. You need to know this, really important. Another things to know, types of operands. What do we mean by types of operands? If you have, this is an AND. I can have here AX or EAX, the extended, and let's say here I can have num1, and then I can say sub EAX and 5. Those are the operands. I have 3 types of operand, and this is also really important. Why? We're gonna see. When I can't do a move, for example, to an immediate value or a constant. This is a constant. I can't do this, but I can do this. I can move a constant to a register. Those are registers. Those are what? What's num1? When you declare something in C++ or C, integer num1. This is a memory location. You named it as num1. So this is memory location. First thing, we have types of operand. We have registers, EAX, AX, EBX, and second one is memory location. This could be here. Registers is this. This is the first type of operand. Registers could, memory location is here. And then we have what's sometimes called as constant or immediate. And some people say constant expression, meaning 5 plus 10, and they put it as a 4th operand, but I consider it as constant or immediate. So think of them as all constants. 3 types of operand, really important, guys. Now we have one more or 2 more things. I need to explain the registers, how we can break them down, and I need to explain the instruction life cycle. And this is really important. You might get it in the exam. This is an L, but I write my L like instruction life cycle. 5 stages. Instruction fetch. First thing, fetch the instruction. If you remember the previous add, and AX num1. Fetch the add instruction from memory. Instruction fetch. Decode the instruction. Instruction fetch. Decode the instruction. Then fetch operand. If I have operand, those are types of operand. Fetch the AX and num1. Then execute the instruction. Do the add operation. Then write back to memory. This is the instruction life cycle. Remember, instruction fetch, instruction decode, fetch the operand, execute, and write back. It's really good to know it in detail. Now let's see how I can break my registers down if I don't want to use what? Remember, EAX was how many bits? Was 32 bit, but this can be broken down. 32 bit is how many bytes? 4 bytes. Remember, 1 byte equals 8 bit. So 32-bit is 4 byte. This is EAX, a 32-bit register. I can break it down to AX, which is what? 16-bit, or 2 bytes, or what's called sometimes as a word. And this can be what? An integer. An integer is 2 byte. A short is 1 byte. A long is 4 byte. And we have to be careful in assembly. If I try to add EAX, which is a 32-bit register, or 4 bytes, plus BX, which is a 16-bit register, or 2 bytes, this will give me an error. Size mismatch. Size mismatch. The sizes have to be the same. So this is AX 16-bit. I'm using only what? This part now. I can also break it down to what? A low, which is 8-bit, 1 byte, and A high, which is another 8-bit, which is 1 byte. So now I can say what? I can say add AL with B8. This is 8-bit and this is 8-bit. There's no problem with that. You can even say A high. We can use both of them. Low 8-bit, that's why they call them AL, and A high. AX, by the way, stands for the accumulator. Extended, remember why? First we had 16-bit machines, then we had the 32-bit machines where I'm using 32-bit registers. That's why they called it extended accumulator. They extended it to 32 bits. And I can do this to the general purpose register. You can do that for the E flag and instruction pointer or the code segment registers. This is an advantage that we can use. So remember, memory hierarchy, know the differences, volatile and non-volatile, types of operand registers, memory location, and constant values. How can we break down the registers? Registers, chapter 2, slide 16. Really important. If you don't know this stuff, guys, you're not going to be able to program. Then, what did we and the instruction life cycle. I think we covered until now, like mostly chapter 1 and chapter 2. I'll try to, we're going to start with the programming part now. I'll post also some slides on, some videos on the programming. Programming is not easy, guys. You have to study real good. Study real good.